The probes we'll be using are a neon bulb with the leads cut off of it, with the glass pointed outward close to the area we'll be probing. And then a 2-volt incandescent light bulb with a bobbin, fiberglass washers with multiple turns of number 26 magnet wire we'll be using for the magnetic field. The E field is measured generally for tuning purposes. This is a 1-inch square piece of copper sheet, which is the center terminal. Is soldered. The center conductor, rather, of the coax, 50 ohm coax, is soldered to the center of the probe. Generally speaking, that has always been used to be about 30 inches out from the elevated capacity. This is up and down to adjust frequency. This coil resonates about 1850 or so in the current arrangement. The distance down from here to here has been adjusted by moving the primary 3 windings to a point where we get a good match to the output of the transmitter, 50 ohms. Now, moving over to the operating position, this is the ICOM 7300, which I've tortured to death over the years. Now we're putting out roughly 30 watts or so in the CW mode. This is how, see if I can get the glare out. 2 traces here. This reading here, corresponding to the A trace, is the E field from that 1-inch square copper sheet probe. This 1.86, that's the current flowing into the ground connection. And it's pretty close to 1.86 amps. This might read just a little bit high, but it's a current transformer. I'll show you that in a minute. That's the B field, and you can see the phase relationship. Now, I haven't calibrated this because of the length of the coax. Could have something that, form a delay line and influence the exact phase. But you can see that it's close to 90 degrees out from the E field to the earth current. Now we'll take a quick look. I'll show you where the earth connection's made. This is in here is a transformer. 1 volt equals 1 amps. When I did this and tried to calibrate it some years ago, 12 to 1 loaded by 13 ohms on a piece of ferrite core. So that's basically the probing and the monitoring, and we'll get on to some tests. We've energized the resonant transformer to about 40 watts of power in its resonant state. Probing with the neon bulb, we see there's no excitation of the neon near the primary windings. We follow up the ground lead. It gets a little hot there with some electric field, and then we come across, remains hot where the connection to the gradient ring is and to the bottom turn of the coil. Now, I'll go up the side, progressing up. You see that it gets weak and hits that null point. Now, it'll light up at the top, of course. Most brilliant at the top, which is routinely the case. But with the bulb excited to its full strength, we come down and we can slowly see the dimming, and then it nulls out, and then it gets reignited again at the base. I'll do that again. With me standing this close to the structure, it's affecting its tuning. So there you go. There's the effect I wanted you to see. So we're coming down and we reach a null point in there, and that's so typical. I don't know, that's about what? 1, 2, 3, 4, 5, 6, 7, or 8 turns up or so. And then it gets down below, it gets hot again down at the base. And it's tough to get a true even distribution with this setup, where you have a quarter wave structure. So we're going to switch probes, and we'll go down again. This is the magnetic pickup and the 2-volt incandescent bulb. And we can't get anything here at the base. On the primary. If we come up along the ground wire, I've seen some excitation here. It's got to get coupled. Right, you really should have a coil going right around this thing if you're going to measure the current in the wire. But this is for general testing purposes. We see a little bit of light there. Again, I'm getting a little close. Let me see if I can. There's some right about there. You can see it light up a little bit, and then it comes down. So there's some magnetic coupling. But inside the coil, you get very good coupling to the turns on that bobbin. The magnetic field inside the coil is so much stronger. And then if we do this, it seems that bottom, the gradient ring, is influencing this. So I'm going to pull the gradient ring off, and we're going to see if we get the same influence. I can put the thing at 90 degrees and it has no effect up here at all. I don't know if I can shoot across. I'm going to get too close to it. I won't be able to do that. Go up inside here maybe. Yeah, inside there with the thing at 90 degrees to it, it's hot too. I'm going to pull the gradient ring off, and then we'll try to see what that distribution looks like. So we remove the gradient ring. I'll just quickly check the distribution of the electric field. Try to keep the camera focused. It seems to be the same. Although the bottom leads do seem to have, the bottom windings seem to pick up the electric field a little quicker. So it may have a positive effect at the distribution. That is the gradient ring. Because in here, you know, the sensitivity of this neon bulb isn't that intensive. So it's interesting. I had trouble picking up the excitation on these lower windings with the gradient ring present. So it may very well aid into the quarter wave distribution. Now we're going to switch probes if I can reach over here and find it. There it is. So again, we'll do we'll come down and we're seeing the similar excitation. Well, this is the one I wanted to see. Yeah, so in there, it still lights up even without the gradient ring, with the winding at 90 degrees. The winding of the bobbin, that is, at 90, whereas this way. So we go up, and that field is oriented differently. At least the lines of force are coupling differently into the winding of the bobbin. Down here, there is no excitation until you go at 90 degrees, where you will see a little coupling. That's interesting. But again, on the inside, instant full brilliance going up. Of course, brightest at the bottom where you would expect it. All right, so that's concludes that. So now we have a different coil form. It's a conical shaped form using the same primary as we were with the cylindrical coil. This has a elevated capacity that has been adjusted. This is resonating at about 1.92 or somewhere around there. A little bit higher than the other cylindrical coil. So we can do the same kind of measurements with the probes coming up, and we get some excitation of the neon coming up the base, ground wire coming in. There is no lower gradient ring on this coil. I have never made one, never have it. And you can see the bottom couple of turns are hot. We go up and it nulls out. We'll start at the top and come down. I can't get too close to this because the phone camera freezes up because of the influence of the coil's field. So we're coming down and we have a gradient that's gradually getting weaker, and then it gets to the point where it can't sustain the glow in the bulb anymore. And the point being is that it gets stronger on the lower couple of turns. Typical, very typical. So we'll probe with the magnetic pickup now. And we'll try to follow the same path up. Of course, this is on the inside, right? This is with the bobbin at 90 degrees. It's hot. On the outside, it's not so hot. It doesn't even light up. On the inside, 90 degrees, it lights up. So if we start at the top, and we don't see any excitation on a little bit right there. That's glowing a little. So there's a little magnetic coupling right there. If I go 90 degrees, it disappears. I come down, disappears. I go 90 degrees and it lights up. So there's a change in orientation of the fields as it couples into this bobbin winding. We go inside, and of course it's very brilliant, very strong, all the way up. And then it does get weaker up the top, brighter as it comes down. I don't know if you can see it in the video or not, but I can see it with my eyes. So I'm going to try to shoot over to the other side, if I can focus at all. And I'm 90 degrees to the inside now, and there's nothing. And I come down all the way to the bottom on the inside, and there is no coupling. On the outside, there is some coupling. On the inside, 90 degrees, there is some coupling. But as you go up on the inside, as I reached over, it showed it. So there's some food for thought. What else can I tell you? This primary is again arranged at this distance. You can see the relative, distance between the bottom of the secondary and the top. That's arranged to give me the 50 ohm feed point that I like to use and that the transmitter is happy with. So there's the second shape. All right, now we have the different form, the cosmic induction generator form. This is 20 inches in diameter. We have a 3-turn primary, 3/8 copper. And again, the same coaxial cable. It's Teflon core, silver-plated braid. That's the same that has been on both cylindrical coils. The conical coil that was just some number 14 stranded with a mil-spec braiding on the insulation. It's almost smokeless when it burns. Anyway, so we'll probe this. This is excited at about 1.97. It's about the same. Funny, it fell right in it where the conical one was resonant. So we're coming up on the ground lead, if I can reach it. And we see we have, it's fairly hot up to the feed point. Now we come here and it's, I don't know if I showed you that. I was looking in a different direction. Let me try that again. I got to keep the camera focused on what I'm doing. I'm sorry about that. And so anyway, we come up here and we notice that it stays intense. It hardly ever goes out, but you can see that same null point exists. It's bright at the bottom turns, coming up, and it gets dim. Now we're almost halfway up the whole winding because this winding is so stout. It's the aspect ratio is a lot different. So the null point happens at a greater percentage up the winding, up the coil, but then it gets bright again. So let's see, we can look at the same thing on the very big diameter primary. Again, the distance here is giving us the 50 ohm feed point. So, let's see, I got to get situated to do this. I don't see any lighting there. We're going at 90 degrees here. The bobbin again is at 90 degrees to the turns, and it's lighting up at the base. We got a little of that in the other one. Oh, that's interesting. So we're getting it at the top on this too. Not at the capacity heads, right at the top winding. This coil has a different distribution of the magnetic fields. We didn't get that on the other ones. That's interesting. So I'll turn to be, in line with it. Now my hand is in the high field, so it may have detuned it. and I get nothing. Let's see if the thing still lights up. I may have detuned it by being so close. Let me come through the primary. I don't know if I'll be able to do this. Yeah, there we go. So again, on the inside, it does get weaker at the top, but on the inside, I'm just moving away from it. That's why it's getting dimmer. I can't get at it with the way the frame is. But again, the inside of the coils, we have a lot of magnetism coupling into this turn. It's tough to probe this without, I need a longer stick, I guess. Anyway, that gives you an idea. And I think the most interesting thing here is that we have this going on. We have, when the bobbin is at 90 degrees to the coil windings, we have that effect. We saw that on the other coils, the higher coils, the longer coils. But this one has it up at the top too. So interesting. Food for thought, fellas.